We're going to look at some examples of games that can be naturally represented as a sum of simpler games. The first example we'll look at is this. The game is just like NIM. There are several piles of stones. But instead of using NIM rules, where you can take any number of stones from a given pile, here we're allowed to remove exactly 1, 2, or 3 stones from a single pile. That's like the subtraction game that we looked at on the very first day of class, or second day of class. Using normal play rules, we'll have the last person to play wins. So our first question will be to ask ourselves, what is the Sprague-Grundy function for this particular game? And once we know that, we'll be able to answer these other questions very easily. What, if anything, is the winning move from an initial position with 5, 6, 7, and 3 stones? What about a position 25, 36, 17, and 4? We'll be able to answer the question for any number of stones. But how are we going to find the Sprague-Grundy function for this game? Well, this game consists of 3 piles. And we already know how to play the 1-pile version of this. That's, as I said, the one that we played early in class. And we first started talking about the Sprague-Grundy function. It was very clear that just for the basic 1-pile subtraction game, with subtraction set one, 2, and 3, like we had with the 21 flags game, the Sprague-Grundy function is what I'll call here g of n equals n mod 4. That just means the remainder when you take n and divide it by 4. So it's going to be 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, etc. I mean, g of 0 is 0, g of 1 is 1, g of 2 is 2, g of 3 is 3, and then we go back to g of 4 is 0. What is the Sprague-Grundy function for our game here? Well, our game is the sum of 3 separate, or n separate if we have n piles, in this case 4 separate subtraction games, each with subtraction set 1, 2, 3. So the Sprague-Grundy function, I'll call it capital G, of a position x1, x2, x3, x4. I'm using x1, x2, x3, and x4 to denote the sizes of the 4 piles. That's just little g of x1 nim sum with g of x2, g of x3, and g of x4. In this case, the Sprague-Grundy function for 5, 6, 7, and 3 is going to be 1. That's the Sprague-Grundy function for the single pile game, starting with 5 stones, nim sum with 2, and 3, and another 3. And we can compute this quickly in our head. This is just the same as 1 nim sum with 2, because the 3 plus 3 gives you 0 in the nim sum. And what's the nim sum of 1 and 2? Well, that's just 3. So very quickly, and we can do this all in our heads, the nim sum is 3. So what constitutes a winning move? A winning move is one where we get the nim sum back down to 0. You can see here the nim sum of 1, 2, and 3 is 0. You might recognize that as a winning position in nim. If you just take all 3 of the stones from the 3rd pile, that's a winning move. Of course, there's another winning move as well. You could just take 3 stones from the 7 pile. That would turn this 3 into a 0, because we would be down to 4 stones in that 3rd pile, and the Sprague-Grundy function, little g here, of 4 is 0, and again we'd have 1 plus 2 plus 3, that nim sum, which would give you 0. So you can either take away all 3 stones from pile 4, or you can take away 3 stones from pile 3. Either one would give you a winning move. Well, what if we started with 25, 36, 17, and 4? Well, again, it makes very little difference how big these numbers are. The dim sums are very easy to compute, especially since the Sprague-Grundy function for the individual piles reduces all the values to 0, 1, 2, or 3. So we can compute the Sprague-Grundy function for this initial setup, 25, 36, 17, and 4, is just little g of 25. So what is 25 mod 4? It's just 1, plus little g of 36, which is 0. That's a multiple of 4, plus the 17. Little g of 17 is 1, and 4 is 0. And this, again, you can easily do in your head. What's the dim sum of 1 plus 0 plus 1 plus 0? That will give you 0, because 1 plus 1 is 0, and adding the zeros doesn't change that. So this is actually a P position. There's no winning move. Any move you make here can be counted by the next player to bring you back to a position with Sprague-Grundy function 0. For this second example, we're going to play a game again with 4 piles of stones. In this case, it will be just like NIM for the first 3 piles, but in the 4th pile, it'll be like the 21 flags game, like a subtraction game where you can take away exactly 1, 2, or 3 stones. So we have 4 piles. The first 3 play like NIM, the 4th one like the 21 flags game. Here's our first question. If the initial setup has piles of size 15, 10, 13, and 11, what is a winning move, if there are any? Well, to understand that, we want to look at the Sprague-Grundy function. Again, I'll call that capital G of the position 15, 10, 13, and 11. And because we can treat this as the sum of games, the sum of the individual pile games, the first 3 are individual NIM piles, and the 4th one is an individual pile using the subtraction game rules with subtraction set 1, 2, 3, we can write the Sprague-Grundy function of our initial position as G1 of 15, NIM sum with G1 of 10, G1 of 13, and NIM sum with what I'll call G2 of 11, where here G1 of n is the Sprague-Grundy function for a single NIM pile of size n, and we've already seen that that's exactly n. For a single NIM pile where you can take any number of stones you want, up to and including the whole pile, the Sprague-Grundy function for a pile of size n is just n. G2 of n, we saw even in the last example, that will be exactly n mod 4, the remainder when n is divided by 4. So G1 of 15 is just 15. We take the NIM sum with 10 and 13. And then we need to know G2 of 11, which in this case is just 3. And then we compute this NIM sum. We look at the binary. For 15 is 1, 1, 1, 1. That's 8 plus 4 plus 2 plus 1. 10 is 1, 0, 1, 0, and 8 plus a 2. 13 is an 8 plus a 4 plus a 1. And don't forget the 3 is a 1 and 1. And we're taking the NIM sum of these, and we get a 1, 1, 0, 1. So this is an n position in this game. How do we play in order to win? Well, we want to modify a pile that has a 1 in this leftmost position because the NIM sum has a 1 in the leftmost position. And we can choose any one of those. We're going to need to change this first position, the 3rd position, and the 4th position, counting from left to right. That means we could, for example, do it by taking the 15 stones and kind of replacing it by something that has a 0 here, leave the 1 here, then a 0, 0. In other words, 1, 0, 0, which is 4. So if we reduce the 15 down to a 4, then we'll have a NIM sum remaining of 0. How do we reduce this 15 to a 4? That just means take this pile of 15 and reduce it to size 4. So remove 11 stones from the first pile. What if it's our turn to play and we're down to 7, 8, 9, and 7 stones? Well, again, we can compute very quickly. G of 7, 8, 9, 7 is going to be 7 nim sum with 8 nim sum 9 nim sum. We need G2 of 7, which again here is 3. And we can look at those in binary. That's 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, and 1, 1. Now we have here 0, 1, 0, 1. Again, this is an end position because the nim sum is non-zero. And we have to alter one of these piles so that the new nim sum is 0. And we'll have to alter one in that position where there's a 1 in the highest position in the nim sum. That would be the third one from the right, that 4's position. And there's only one entry, this first entry, in which we have that. And we have to change that by altering the position in that in the 4's column. And we also need to alter the position of the 1's column. In other words, we need to move the 1, 1, 1 down to a 0, 1, 0 to get rid of these two 1's there. How do we do that? We change the 7 to a 2. So we remove 5 stones from the first pile. And we'll be left with piles of size 2, 8, 9, and 7.